Please welcome the next speaker, Adrien. He's going to talk about Tower.
Hello, everyone. Thanks to the organizers for having me. I've been working in Rust for about 3 years now, mostly contributing to Quikwit. Quikwit is an open source distributed search engine for log and traces. We'll be presenting tomorrow in the monitoring and observability room. And if you want to follow along, you'll find a slide on this website. There will be quite a bit of code during the presentation, so that may be easier. So as you know, today we're talking about Tower. It's a crate for building modular networking clients and servers. If you're using widely used crates in the Rust ecosystem, such as Axum, Warp, Tonic, you're using Tower under the hood. Maybe you don't know it, and everything's based on the service trait that I'm going to describe at length during this talk. But before I do that, I would like us to take a step back and think about why we would need Tower. So I want you to think that you are a web developer. You're working with any web framework in imaginary dynamic language, and you ask to write a simple handler to get a user from a database. So you probably would come up with something like this, a function that you would call get user, that would take a request in, add some logging, get the user from the database, save the response, log again, return the response, you're done, and you're pretty happy. Pretty quickly, you would realize that maybe there's another way to do it. Maybe you could decouple the fetching the user part that's strictly about the database and all that stuff from the logging. Like the pattern was, I'm going to log something before the request, and I'm going to log something after the response. Doesn't need to know about everything that's user related. So maybe you would write two functions. The first one would be with logging, that would take two parameters, the request still, but also a handler that would be a generic function that returns accepts a request. And then you would write your get user separately. It'll be a bit more simple, very focused on what it has to do. And then you would compose your with logging function with your get user function, and you would achieve what you had achieved before. But now you have that other function with logging that you can use for like all your enders. And isn't that the essence of programming? We want to write generic and reusable functions that are really easy to compose. For the purpose of this talk, we're specifically interested in decorators. So the decorator pattern is basically when a function or a class wraps on another function. It applies new behaviors before or after calling the inner function. It doesn't know about that inner function. It's totally opaque, and it doesn't matter. We don't care. It doesn't modify the behavior of the inner function. And you've used decorators sometimes with different names, very often middlewares in the context of client and servers, proxies. This is a term that's coming a lot. And then what you can do with those is you have your handler at the bottom. You can also call it a leaf, and you stack middlewares with different behaviors on top of it, and you apply different behaviors depending on what you need. And then you can build a nice library of middlewares that you can share, that you can use from different libraries, and so on and so forth. In that example, we were using a dynamic language. It was really, really easy to do. Duck typing gives us great flexibility. We don't really care about the types of inputs and outputs. When we code, we think about it. Do they match implicitly? If they do, we think it's going to work. We ship it to production. We cross our fingers. But implicitly, everything should match, and then everything should work fine. So this is what we're trying to do with Tower in the Rust ecosystem. But this time, we still want to compose functions, but we want to do it in a very type-safe manner, and we want to be still very flexible. And this is when the Tower service trait comes into play. It is the common interface that allows us implementing components in a protocol-agnostic and composable way. So let me describe the trait. It has one generic parameter, request, It's called request by convention, but it can be any type and anything. An associated type, response, same thing, called response by convention, but could really be anything. Error type also could be anything. And finally, a future type. The future type is constrained by the future trait, so it has to be a future. And you'll notice that the output of the future is fixed for you. It has to be a result of the response and the error that you defined. So your only choice is choosing a future type. The output is already chosen when you say, I want this kind of response, this kind of error. And then in the trait, you have two methods, the poll-ready function and the call. Call takes itself mutably, accepts the request, return a future, like the future you defined. So your mental model should be much easier than this trait. It's just simply this is just a generic async function. This is the same thing. The trait gives us that flexibility that we wanted and gives us the type safety that we wanted. But really, this is the mental model of what is a service trait. With a little twist, you have that additional poll-ready function that needs to be called once before calling call, and it provides a way to provide back pressure to the caller. So the poll-ready implementation for a service without any external dependencies for the hello service that we're going to define is really simple. Poll-ready return is always ready and returns OK. If you're implementing something else, if it's not ready, you return pending. And later on, the task will be polled again, and hopefully it'll be ready. If you're writing a service that has an external dependencies, for instance, you depend on a database, you need to acquire that database connection. So all the services that have external dependency need to load up upfront the resources they need, and so they can say when they're ready or not to the caller. So in this example, if we haven't acquired yet connection, we will pull our pool of connection to acquire a connection. We will save it mutably in our internal state. And then later, in call, we actually consume the connection using take. So that's why the tower trait is mutable, because it's not necessarily stateless. It can be stateful, so you can manage your resources. And you see with this example why you need to call poll-ready always at least once before call. And for the services that are middlewares, so they basically wrap an inner service, usually implementation is really straightforward. You just delegate to the inner service, so you call poll-ready on the inner service, and you're done. So if you're not doing something too fancy in your service, usually it's going to boil down to those three use cases. So it sounds simple on paper. Why does it get complex? I think people are a bit afraid of like tower and tower services in general, because they use a lot of generics. So it's a bit, it's not always easy to write. It's even hard to read, and it's even harder to write. It's using all the Rust construct heavily, so you have to be comfortable with lifetime, sensing market traits, what is async. It's going to expose you to that. So if you've been using Rust as a better C++, trying to avoid those concepts, writing tower services are going to be a bit challenging. But once you get more comfortable, it'll be very rewarding, because you're going to be exposed to those concepts, at some point, muscle memory is going to help you, and you're going to feel more and more comfortable, and you're going to get, at the end of the day, a better Rust programmer. And in some cases, if you start writing your own features for your services, then you need to know about future polling and pinning, and again, it gets very complex. So the only way to get better at understanding services and writing them is just to start simple with like a hello services and build upon until working like more complex services. So this is exactly what we're going to do during the rest of the talk. So let's implement hello service together. Remember, the mental model is just this hello function. This is what we want to do, but we want to do it the tower way. So the input parameter is the hello request. The hello response will be returned, and we're trying to implement that simple function. So we start defining a health struct, and we start implementing service for it. The input parameter is hello request. The response type is hello response. The error is going to be a little bit specific here. It's going to be infallible because we're never gonna fail. We're just printing stuff. And now we have to choose our future type, and we have various options. And the first thing we can do is go with a box future. We can define our own type alias, or we can reuse the type alias from the future scrape, for instance. And why would we do that? When you get started with writing your own Tower services, I would recommend starting with that because it's pretty easy, it's very readable. The cons are you pay a small fee for allocation and dynamic dispatch. It's fine if you're not, if it's a client or server that doesn't have like an insane amount of QPS, it's totally fine. Sometimes people are afraid of allocation and dynamic dispatch. If you're working on a client or server that does networking and I/O, we're talking milliseconds, that allocation dynamic dispatch is going to cost you microseconds, maybe even nanoseconds. So you should not worry too much. And if you start worrying, you should measure before going for the box stuff. I would want to say though, writing your own future is way more fun. So sometimes I still go for my own future, just my own personal fun. So box futures are good choice for applications, less for libraries, because when you're writing libraries, you want to decide the users of your libraries, whether or not they want to incur some overhead. So it's better if you don't use box future in your libraries so that people can opt out of the overhead. So in this example, we opt for box future. We need to notice that this box future has a lifetime that we'll choose, and it has to be sent as well. That will become important later. So we choose the static lifetime. The Tower service rate is not generic over a lifetime, so we have to go for static. Then we write poll ready. It's always ready, so it's pretty straightforward. And then we write our future. So we declare an async move block in which we build a message and build a response. And then we box that future on the heap. We pin it with box pin, and we should be done. This is how you would unit test that service. You instantiate it. You call ready. We're using the extension trait that makes it a bit easier to work with. So you call ready, and then you call, and it works. So it's obviously a bit more complicated than just writing that hello function that I showed at the beginning, but it's totally doable. When it comes to choosing a future, sometimes you have the choice to choose one from a third-party crate. Futures has some ready-to-go futures that you can use. Tower has a few as well. So sometimes those futures are going to fit your use case. You don't have to go for the box. You don't have to go for implementing your own. You can just reuse one. It's convenient. So in this example, we can use the ready trait from the futures crate. So this time, you do see my pointer crate. We changed the return type here. It's ready, and this time we return ready. So we got rid of the allocation and the dynamic dispatch. And it's actually more readable. So we built a simple hello service. We're going to build a middleware on top of it. That's our logging service. We want our logging service to work with our hello service, but ideally we'd like it to work with like any kind of service that implements the trait. So we're going to make it generic. So logging has an input parameter called S that will be the inner service. And we start implementing service for logging. What we want to do is call on the inner service, and we can only do that if it's the service itself. So we need that bound. And we say the inner service is also a service generic over R, our two generic types here. Then we implement poll ready. We delegate to the inner service, pretty straightforward. And then we implement call, starting with using a box feature. So we build the inner future, calling call on inner, and then we create our own future using an async move block. We do the logging, we evaluate the future here. So here on this line, we build a future, but it's not evaluated. It's actually evaluated here. Then we do the logging, and we return the response. We box pin the other future, and now we go back to our terminal. We run cargo test, and it should work. Except it doesn't. We've omitted a little technicality, and that technicality is coming from what I've said before. The box future must be sent, so the future that you return must be sent. So the inner future must be sent as well. And so we need to tell the compiler that constraint. So we not only we have constraint the service S. We told the compiler it is a service. We also tell the compiler the future that inner service is going to return is also sent in static. And now this time it works. So this is how you would instantiate your logging service. It's wrapping the hello service, and then you call it the exact same way. It's obviously not going to show up during a unit test, but now you have logging on top of your service. And that logging service is usable for some other services. Tower HTTP has a bunch of services that are ready for metrics, tracing. It works a lot like that. So we're going to do this again, this time rolling on our own future, but because it's fun, and because when you're going to read code from Axum, Tonic, you're always going to encounter those handwritten features, so it's good to get used to them. Unfortunately, writing a feature from scratch is actually non-trivial because of the whole pinning thing. And this is not a talk about writing features and me explaining to you pinning, because I don't totally understand it myself. But I can be very practical and tell you how to do it. And I'll show it to you right now. So now the logging is going to happen in the future. So before we were wrapping a service with a service, and the idea is the same. We were going to wrap the inner future with our logging future, so we can add behavior to the future. So you can add behavior to your service, but you can also wrap your future and do stuff after you're done polling or before you're about to poll the future. And this is what can be tricky with Tower services. Is sometimes if for instance you take rate limiting, there's a bit of logic in poll ready, there's a bit of logic in call, and there's a bit of logic in the future. So it's hard to understand where's the logic that's related to the business, what you're trying to achieve, versus what's just related to trying to write a service. So that comes. That's also part of the complexity of dealing with Tower services. So, but back to our logging future, it's going to wrap another future. So it's going to be generic over F. We need to use the create pin project to pin the inner future. So that's why you have the pin attribute there. And now that's how our service, the logging service now is going to look. We replaced the future type with our logging future, and which relies on the inner future, so S colon future. And then in call, now when we are called, we do the first logging statement, then we build a future, and when the future will be pulled already, then this is when we'll actually add the last logging statement. So this is how you implement future for logging future. Same idea, we need to add that constraint and tell the compiler the inner future is also a future. Its output is the output of the inner future. We need to project. I don't know where the term comes from, but you need to project self. And usually the convention is to call this. And this gives you the same object, but when you use the inner futures, they're actually pollable. Because poll is not defined on the future type, it's defined on a pin future. So that's why you need to project which pins the future, which allows you to poll it. Those are the technicalities that you have to deal with when you're writing your handwritten function. But once you've done that, it's exactly like writing normal code, I want to say. So we pull our future, and if it's ready, we add the logging statement. If it's not ready, it means it's pending. It's going to be pulled again later. And also we know that when a future is pulled and it's ready, it will be no longer pulled. So we know that this statement will appear only once. So let's build on top of that. Let's build a timeout service now. So same thing. We want to add a timeout to any service. So also generic over S. But the timeout service is interesting because the logging service is pretty simplistic. It doesn't mutate or touch anything in the request, not in the response. It's like data go through it. The timeout service is a bit interesting because you have to signal the timeout somehow in your return type. And the way you're going to signal the error is potentially using an enum. And in that enum, you will have two variants. And the first one would be the timeout. If timeout occurs, that would be an error. But if the inner service returns its error itself, you have to wrap it in inner. And then the caller will know if the error comes from a timeout of the inner error. That looks like a good idea to do it this way, and you can totally do it this way. The problem is like if you adopt this pattern for like timeouts, authentication, rate limiting, the nesting of all those errors, inner, is going to become pretty complicated and really hard to compose and not easy to deal with. So what libraries usually favor is boxing. So if you use the tower services that modify the error type, they will return the tower box error. And it's much easier to compose. The downside is at some point you have to downcast the error to know exactly what happened. So we're going to use this error type this time to implement our service on future. So it's very similar than before. The difference this time is the error needs to be boxable. So we tell the compiler, I can only be a timeout service for services where the inner error is boxable. The polarity is it's a little bit annoying because it's still delegating to the inner polarity function, but you must not forget to convert the result that is a S error to a box error. So that's why the result returned by the inner service its error must be mapped to the box error. So that's why we need this. Now we implement call. So we take a look at what we do as for our future. So our timeout future is very similar to a logging future. It just wraps two inner futures. One will be used to for the inner future, and the other ones will be for the sleep future. So the sleep future, you can reuse the future from Tokyo, for instance, if you're using the Tokyo runtime. So call becomes pretty simple. All you have to do is build your inner future and your sleep future and create your timeout future, which we're going to implement now. So the core of the logic this time lives in the code of the future itself. So some libraries, they sometimes split the service implementation in one module, and they put the future in another module. So you open the service, and you're like, what does it do? Because everything happens in the future. So you need to understand that sometimes a lot of the work is actually done in the future. And it's the case for timeout. So implementing future for timeout future, as before, we project self into this. We pull the first future, the inner future, and if it's ready, great. It's not a timeout. We return pull ready with the result. We don't forget to map the potential error into its box. If the inner future is not ready, maybe it's taking too long, so we need to verify whether a timeout occurred or not. So we pulled timeout future this time. So if it's pending, nothing to do, we'll be pulled again, we'll go this work again. If it's ready, it means this is an actual timeout, so we need to return the timeout error. And we return elapsed error, but boxed, hence the hint two. So now we're going to see how you can stack services together. I could obviously stack my timeout on top of my LO and then add the logging on top of it, but I can also do it with services that are already ready in Tower. So I import them directly. So I import the concurrency limit, the timeout, and I compose my service by wrapping everything on top of each other. So I instantiate service, I add a concurrency limit on top of it, and then a timeout, and then the logging. So that involves a bit of boilerplate, but it's not too hard to do. What's really tricky, and the compiler is not going to help you with that, is the order with which you wrap your services actually matters. You really want your logging to be on top. If your logging is like logging how long it took, you don't want logging to be in the middle. You really want it to be on top to capture the whole life cycle of the request. And it's probably the same thing. You want timeout to be applied above everything that's doing rate limiting. It would be better to if you had like a notification service, it would be better to put it pretty high up, because if you have services that are below it, maybe they can do whatever they want. So this is what's tricky when stacking layers, and the compiler is not going to help you there. So you gotta be careful, and you can hopefully rely on a good reviewer for like a double check. I wanted to leave a lot of time for questions. This talk is called A Deep Dive into Tower. I realized that in 30 minutes, it's actually not that easy to cover everything that we could cover when we talk about Tower. So let's just call it a shallow deep dive into Tower. So if you want a real deep dive, there are really good resources out there. 2 years ago, not that much, but there's really great content, blog posts and YouTube that I'm gonna talk about a little bit, that really can help you get really, really comfortable with Tower. So there's something that I don't talk about today called a layer. Tower people are pretty obsessed with composability. So a layer is a way to compose a stack of services. A service builder is a way to conveniently build small stacks of services. A service builder helps you get rid of the boilerplate to write this, for instance. So if you want to keep studying Tower, I would start with layer and service builder. Then I recommend reading Inventing the Service Trait. That's a blog post by David Peterson, who's a Tower contributor. It's a really good introductory blog post, so maybe you can start with that. It takes about 15 minutes. I found that the Axum documentation page about middlewares is really, really good. So I think that's a really good resource. And then in the spirit of building and reading and writing services that are more and more complex, I think the next step for us is looking at the rate limit service. The concurrency limit is also a bit more complex, but really interesting. And then you can look at the channel from Tonic. It gets pretty complex as well. And then if you really want to take it to the next level, I think the pool in Tower. So here we're only showing that a service that wraps just one service, but now you could wrap multiple services, and that's what a pool does. And the pool is a service, it wraps multiple services, and it's using pool ready to track the load of each inner service to handle back pressure. So it's a really interesting use case of like using pool ready in a very fancy way. So pool is also very interesting. Good videos on YouTube. Also David Peterson, he has a Java stream about Tower. He goes through the same thing. There's a hello and the logging and the timeout, and you see him dealing with like all the little things, because obviously on presentation I get everything right on the first try, but it's not exactly how that happens when you do it yourself. And if you want to get more comfortable with async await in Rust and futures in general, John has a great talk on YouTube as well. And you'll find those resources on the slides that are available at this link.
Back in the first few slides, you mentioned the poll ready function, and you were initializing a database connection. I didn't get it if the database connection is actually a future or not, because the poll ready function doesn't return a future.
You talking the database one?
Yeah, just where you initialize the connection.
Yeah.
You know, you depend on a connection.
Yeah, it has to be a future. I mean, no, it doesn't return a future, but because
That one, yeah.
yeah, this one. Yeah, I'll pass quickly because it's a bit complex. So poll ready doesn't return a future, but it behaves like one because you pass it the context as the waker, so you can rebuild future really easily.
Yeah.
With access to the context.
Cool.
And I'm happy you asking this question, because if you look at the let's come back here. Talk about the concurrency limit. The concurrency limit uses a semaphore. So a naive way of implementing poll ready with a semaphore would be to call try acquire. And if you get the permit right away, it's cool. Poll ready is ready, and you just save the permit, and then you get rid of it in call once you're done. But a better way to do it is to start polling the future. You don't call poll ready, you call ready, and if it's not ready yet, it's okay. You still maintain that future that started acquiring a permit. You save it. You save it in your internal state, and then the next time you keep polling that future instead of each time doing try acquire. So it's really nifty trick that you can see in the concurrency limit service.
Okay, cool. Thank you.
When is Tower going to go version 1? Because now it's on 0 and Hyper just dished it because it's not 1 yet.
So I'm not a Tower contributor, so I don't know exactly. I think they're waiting for the compiler people to give us the full story of what async is gonna become. You'll see that with the last release of Rust, now you can return an implement future, but there's still like whether it's set or not to deal with. So eventually, I think they're waiting for see what we can do in Rust, and then once the whole async work is stabilized, I think they will come up with a new version of the trait, like with those new constructs that are being released and will be released in the next version of Rust. We can greatly simplify the service trait. So they will wait for those features to land, revise the trait, and then release 1.0.
And the second question, is there a way to make this Tower layers, let's say, optional, so you can disable them from maybe outside the code, from the compiler somehow?
Yeah, I mean you could use there would be different ways. You could use like feature flags. You could use environment variable. Like services have a state, so and they're mutable. So you can do what you can do. You can do a lot. You could have a shared atomic boolean somewhere in there, and you can enable, disable it.
Thank you.
Yep.
On the timeout future slide.
What? Timeout future. This one?
Yes, there's a poll function, and if none of them is ready, it will just return. And how would it know when to call it again? Like you polled once, and none of them is ready yet. And
It's the runtime is going to take care of it.
how?
With well, it depends on the runtime you're using. It knows it's not ready, and then then we're talking about how you implement a runtime basically. It maintains like a queue of futures, and it regularly pulls them using some a waker, which it's using that context, using the waker. When it's ready, it's gonna call the waker. That's gonna wake the runtime, so on and so forth.
Okay.
But you, as an implementer of the future, you're not in charge of like telling when you should be pulled again. You're just in charge of saying I'm ready or I'm not. That whole machinery is left to whoever implements our async runtime.
Okay, thank you.
Thanks for the talk. I had a question because you mentioned that there was some overlap between implementing your own future and the tower service trait itself proposing like a pull function and a pull ready function. Is there any reason, apart from fun, to implement a future trait yourself? Like, is there any benefit from dealing with the internals of creating a future versus implementing your whole logic inside of the service trait itself and just using the basic tower or basic futures, future types?
You mean the box futures?
Yeah, exactly.
Your question is like, why would I bother writing my own future when I can use box?
Yeah, when I have this pull function inside of a service trait itself where I can bake my own logic and not have to deal with, projecting my pins and so on and so forth.
I'm not sure I totally understand your question, so my answer might not satisfy you. I think you're right. You want future if you're writing a library. You don't want your users to incur the overhead of like the box future. You write it if you have like some constraint that might be related to performance that is going to push you to write a hand-rolled future that doesn't allocate, it doesn't have dynamic dispatch. Yeah, that would be my answer. I think it also depends on your team. If you're the only guy in the team that's going to understand like, oh yeah, I project the future and I use spinning. If it's just you, maybe you don't do it. It depends on those constraints.
Okay, thanks.
Awesome. So if there's no more questions, let's thank our speaker.
Thank you.